Let's look at a circuit like this. These are two capacitors, C1 and C2. This is a single branch. We have another branch here, say of C3 and C4. And these two branches are connected between terminals A and B. Nothing difficult about this, right? This is a series connection of C1 and C2, another series connection of C3 and C4, and these two branches are in parallel. Any calculation you need to do is not going to be anything difficult. But let's consider applying a potential difference of V between A and B. I ask you what is the potential V1 at this point is, that is the potential difference across C2. This end is at 0, so potential difference across C2 would be the potential here. Similarly, if we call this V2, the potential difference across C4, right, would be the potential V2, because this is 0. Now, since in a series connection, the potential difference will be in the inverse ratio of capacitances. So if you are asked what is V1, you would say that is the potential difference across C2. Since V divides in the ratio of C2 is to C1, inverse ratio C2 is C1, this is C1 part of V. As it's divided the ratio, C2 is to C1. So V1 will come out to V C1 by C1 plus C2. Similarly, V2 will come out to V C3 by C3 plus C4. Now, if V1 is equal to V2, this V1 is equal to V2, that is V C1 by C1 plus C2, if it is equal to V C3 by C3 plus C4, that would give you what? Invert this. This is C1 by C1 1 plus C2 by C1 here, and this invert that. V gets cancelled, of course. C3 by C3, that's 1 plus C4 by C3. That is C2 by C1 is equal to C4 by C3, or maybe you can put it more like C1 by C2 is equal to C3 by C4. So if this ratio C1 by C2 is equal to C3 by C4, then these potentials will be equal. So if these potentials are equal, anything that you connect between these two, say we connect a capacitor C5, there will be no charge on that. So the capacitor C5 doesn't store charge if, well, C1 by C2 is equal to C3 by C4. So it doesn't exist. If you see a circuit of capacitors like this, if you find the ratio condition is satisfied, though there are two junctions here, there is no flow of charge that way, you can ignore that capacitor and that's it. Well, it becomes a simple circuit. You do see some situations like this. So when you do, well, you don't solve for V1 and V2, you just look for that C1, C2 ratio, if this ratio condition is satisfied. If this condition is satisfied, ignore that. These two are in series, find the equivalent capacitance. These two are in series, find the equivalent capacitance. They are in parallel. So simple enough. 4 plates are arranged like this. They are all of equal area A each. The gaps are equal D each. Any set of conductors, well, with one set having positive charge, another set having negative charge, will form a capacitor. So we would like to find the capacitance of this system. This is not a regular series parallel kind of arrangement. Something else has to be done here. We go to the very basic question. What is capacitance? The ratio of charge stored to the potential difference applied. Let's imagine a potential difference of V is applied between A and B. This is V and this is 0. These two conductors are connected to each other but not connected to either A or B. So let's assume the potential of this is V1. This will be different potential. So we know the potential difference between the pair of conductors. This is V minus V1. We'll assume V1 is between 0 and V. This will be V minus V1. This is V1 and this is V1. So this is again V minus V1 there. And this is V1 and this is 0, V1. So we have knowledge of charges on these plates in terms of the potential differences between the gaps. So what will this be? This will be, well, you can work that charge out by saying there is a field of V minus V1 by D upward, right? From higher to lower potential, V minus V1 by D. And this should be equal to, if there is charge of density sigma 1 here and minus sigma 1 here, the field in the gap will be sigma 1 by epsilon 0. So sigma 1 by epsilon 0, and what is then sigma 1? Epsilon 0 into sigma 1. And we are interested in Q1, the charge there. There will be sigma 1 into well, A, which will be sigma 1 is what? Epsilon 0 into V minus V1 by D into A. This we called C, right? Epsilon 0 by D is C. This is C into V minus V1. So what is the charge here? C into V minus V1. How did we get this? From, we have assumed potentials. So we know the potential differences. In terms of potential differences, we know the field. So once we know the field, we know the charge responsible for that field. The charge is, mind you, these two layers are equal and opposite, and the field in the gap is upward here. These two layers are also equal and opposite, but the field due to them is confined to this region. The field due to these layers outside will be 0. They are equal and opposite layers. So same thing here. These layers produce field in this gap. The fields produced by them outside cancel out. There will be no layer here on the lower side of the bottom plate, and no charge on the upper side of the top plate. Then we got that charge there, C into V minus V1, where C is the epsilon 0 by D, that's C. And what is the charge? This is V1 and this is V, so this is V minus V1, so there will be a negative charge. This is negative, right? Minus, this is 2, because the same situation here. This is V1, this is V, this will be positive and this will be negative, so this is the charge. And what about this? For the charge here and here, this is 0 and this is V1, so V1 is greater than 0, we'll assume this will be plus CV1. That will be 0, right? So we have charges here on this surface, on this surface, and this surface, and we got that charge as this. And what do we get here? This is minus 2V1 plus V1, that's 3V1. And this is minus 2V goes to the other side, and so this is 2V, and we got V1 in terms of V, 2V by 3. And what else? Now the equivalent capacitance between A and B is charge stored on the system, right? Charge stored is charge that is flowing through A, or that's charge that is left through B. B is convenient because there is only one surface on which charge is present, and here there are two surfaces. So it's simpler here to say there is minus CV1 here, so CV1 is left there. CV1 is a charge that is flown through B, and if you add up these two charges, the two layers, you will get the same thing. CV1 by V, right? And what is V1 by V? 2 by 3. So this is 2C by 3. That's the effective capacitance. If you wanted to look at the terminal A, when A, plate A, the charge on the upper surface is C into V minus V1, right? And the bottom surface also is same, so this is 2C into V minus V1 by potential difference, that is that V minus V1. What is V1? 2V by 3, so this is V by 3. So again, you get the same thing, of course. So it will be more convenient looking here because you don't have to add up the charges on two layers. It's come out to be convenient here because on both sides you have conductors at V1, so it's come out to be very convenient. So otherwise, so this is also 2C by 3. This is the effective capacitance between A and B. We can also assume charges and then find the equivalent capacitance. We'll assume charges and find the potential difference in terms of the charges. Let's say charge flows in through this and the charge of density sigma 1 collects here. This plus sigma 1 because this is a lower potential terminal and this higher potential terminal. Let's say this layer is sigma 2. We'll assume as many labels as necessary. Facing layer must be equal and opposite. This is minus sigma 1 and this sigma 2, so this is minus sigma 2. This minus sigma 1, so total charge this must be 0, that will be sigma 1 plus sigma 2 here. And this will be minus sigma 1 plus sigma 2 and charge leaves through B. This is minus sigma 1 plus sigma 2. Now we can write a simple relation here, and well, the field here is sigma 1 by epsilon 0 this way, right, upward, and here it is sorry, this must be sigma 2, and this will be sigma 2 by epsilon 0 downward, right, this way. And this potential and this potential are same because they're connected. So what do we do there? The fields here and here must be equal. So you end up with sigma 1 by epsilon 0 equals sigma 2 by epsilon 0. How do you do that? What is the potential difference here? Sigma 1 by epsilon 0 into d. This is the higher potential. The same thing here, sigma 2 by epsilon 0 you will get, right, into d. Because, well, this potential difference here must be same as potential difference here. Why? These are equal potentials. These are connected conductors. So this potential difference between this plate and this must be same as this. So we will get sigma 1 by epsilon 0 is equal to sigma 2 by epsilon 0. So sigma 1 is equal to sigma 2. And what else do we need? That's it. C effective is how much charge? Sigma 1a plus sigma 2a. That's sigma 1 plus sigma 2a by potential difference A and B. How do you get that potential difference? Start from here and you're going with the field downward. So that potential difference will be, it will be a drop of this much. And then you have to go from A to B, right? So you got to go through this gap, the decrease in potential of sigma 1 plus sigma 2 by epsilon 0 into D. This is the charge. Substitute sigma 1 is equal to sigma 2 here. This will be, let's say sigma, just for convenience. And this will be 2 sigma A. This is again 2 sigma, so that will be this 2 sigma, right? 3 sigma by epsilon 0 into D. Sigma gets cancelled. Epsilon 0 A 2 epsilon 0 A by 3D. Well, epsilon 0 A by D we called it capacitance in adjacent plates. This is 2C by 3. This is another way of working it out. So nice. Well, you can assume charges and find the potential difference. The rule for potential difference we found was this. We could find the potential difference between this plate and this plate, which should be 0, because we'll travel this way. When we went against the field, the potential increases, and then when you go with the field, potential decreases. So we ended up with saying sigma 1 is equal to sigma 2, which is fairly simple. Start from here, go along this path. There is an increase in potential of sigma 1 by epsilon 0 into D, and then there is a decrease in potential of sigma 2 by epsilon 0 into D. If you go with the field, potential decreases. If you go against the field, potential increases. So this sigma 1 by epsilon 0 into D, and this is sigma 2 by epsilon 0 D, and you're ending up with this. Because these two are connected, the potential difference calculated that way must add up to 0. So this is the way you can work it out. This time let's do some redrawing and then show that they're actually in simple series parallel. Not always does it work out, so trying to redraw may not always yield the results, because it may end up without being simple series and parallel, and you then have to do calculations. Let's see what we can do here. Let's call these plates 1, 2, 3, 4. There is no charge on the upper surface of 1. There is only charge on the lower surface, facing surfaces. There is no charge on the bottom surface of 4 either. So what do we have here? There is a charge here, positive charge, negative charge, and then there is a positive charge there. We are assuming a potential difference of V between these two. So, but then we are seeing what? This is 1, and this is the upper surface of 2. These two form a capacitor. So for convenience, we'll imagine drawing it like this, 2 surfaces separately. This is 2 lower. 2 lower forms a capacitor with 3 upper. This is 3 upper. And then 3 lower forms a capacitor with 4. 3 lower, and of course they're connected, of course. Then this is 4. 4 charge is stored on only one surface, so we're not showing this upper and lower. And what are connected? 1 and 3. So let's show this connection like this. 1 and 3. They're connected. There are one capacitor here, one capacitor and one capacitor here, and this is where you want the equivalent capacitance between A and B. Let's see what we have between A and B. If you consider these two junctions, there is a path here of C, capacitance is C there in that path. There is capacitance of C here. So that they're in parallel, that's 2C. That 2C is in parallel with C, right? You can replace all this by C and C are in parallel, 2C, 2C and C. So C effective is 2C into C by 2C plus C, that is 3C, that is 2C by 3. Done. So what have we done here? We have shown this surface separately as one plate because that's how we're accustomed to seeing capacitors. This plate stores charge on either side, this plate stores charge on either side, and this one stores only the charge on the upper surface, this one stores charge only in the lower surface. So 1 and 4 have been shown just as it is, but 2 and 3 have been shown as, well, two separate plates, for one for positive charge, one for negative charge. So if you see this kind of a circuit, you would say, yes, I know how to calculate this by using simple series parallel connections. It doesn't work that way always, so it's a bit risky, but it's fun to see it this way when things are not that difficult, simple, and not too many plates there. 5 large plates of equal area A each are arranged at equal distance of D each. Well, what is the capacitance between A and B? That's what the connection is. You can see that 1, 3 and 5 are interconnected, and 2 and 4 are interconnected. You assume a potential difference of V between A and B. After all, capacitance of a system of conductors is the ratio of charge stored to the potential difference applied. So let's assume a potential difference and find how much charge is stored in the system. This is V, and say this is 0. Now, if this is V, this plate is at V and this is 0, so the charge here will be plus CV, right? This is CV, we have learned this already. In terms of V and this epsilon 0 by D gap and this epsilon 0 by D capacitance, we can find the charge as CV. Also, you notice all the conductors are accounted for in terms of potentials. There is no conductor not connected to either A or B, so these are 2 conductors connected to B, so potential is 0 for them, and these are 3 conductors connected to A, their potential is V. Connected conductors have the same potential, right? Then this is CV. Let's just go to the positive plates, and this is positive plates, and these are the ones with higher potential. We're assuming V is positive, and so this is V and this is 0, so this is plus CV again. And here this is 0, this is V, so this is plus CV. And there will be minus CV here on both surfaces. You have minus CV, this is again minus CV, and this will be plus CV. So this is plus CV, right? This is V and this is 0, so there will be plus CV. So we've got all the charges on the surface of plates connected to A. There's no charge on the upper surface of this and lower surface of this. So the charges here are minus CV, minus CV, minus CV, minus CV. So there are 4 surfaces there which are storing negative charge, and 4 surfaces which are storing positive charge. There's no charge on these 2 surfaces. So charge that is flown in through A is 4 CV. It's gone some this way. 4 CV, where C is epsilon 0 A by D. That way potential difference applied is V, so this is C effective. This is 4C, that is 4C is epsilon 0 A by D. That's interesting, right? It's come out of very simple because plates are either connected to either A or B, so there is no unknown potential to assume and write equations and solve for. This is a fairly standard arrangement. Alternate plates connected together. You can have more, 7 of them, and say alternate plates are connected together so that adjacent conductors have the same potential difference. So that's how this capacitance, if there are n of them, n of these conductors, all of equal area and cap D, will be n minus 1 capacitors, and this will be n minus 1 epsilon 0 A by D. I'm assuming area is same and gap is D for simplicity, but essentially, well, that's what you get. Effectively, they are in parallel because everyone has the same potential, every capacitor has same potential difference, and if potential difference are same, it's like parallel connection. You can actually redraw this and see a parallel connection, but it's not necessary. I think it's simple enough to see.